We left off last time talking about standing waves, and we got through most of what I wanted to get through. There's just one more thing that I wanted to talk about, which we didn't get a chance to talk about, and that's the energy in a standing wave. So let me just pull up the end of the last lecture just so I make sure. Yeah, so we talked last time about, I gave you formulas for the wavelengths of the harmonics, and we came up with, I explained how we got those formulas, and you could figure out how to do that in general. The last thing to talk about, like I said, is standing waves. So let's talk about, the energy in standing waves. So let's talk about the energy in standing waves. So the energy that we get in a standing wave might seem a little bit paradoxical. So the first thing to think about is, for a standing wave, for a standing wave, it's just two waves coming towards each other. And waves don't the waves shouldn't cancel each other out. Like the energy doesn't just go, if the energy, basically the energy can't be lost. There's no friction or anything that's causing energy to be lost. So on one hand, one might think that the energy in a standing wave is equal to twice the energy of the traveling waves, because there's just two of them, and we're assuming that they have the same amplitude and so on. So that would be a good guess, but we can also think about it a different way. Let's instead consider we're considering two oppositely traveling waves, each with amplitude A. And let's consider just so we can make this concrete, let's consider the second harmonic for fixed end standing waves. Just so then we can have a picture. So the picture here is, you have your cavity, and then the fixed end that's terrible. The fixed end second harmonic it just has precisely one wavelength through it, and then it oscillates up and down, right? So each wave has amplitude A. So this distance here, this distance would be 2A. Each traveling wave has amplitude A, that is. So, like I said, the total energy should just be twice the original energy. So that would say that the energy in the standing wave should just be proportional to A squared. I don't know why I'm putting this in parentheses. Should be proportional to A squared plus A squared, which is 2A squared. So if you double the amplitude of each of the traveling waves, you quadruple the amplitude of the resulting standing wave. But the standing wave itself has an amplitude. The standing wave has amplitude 2 times A. So wouldn't the energy just be proportional to that amplitude squared? So that is to say, which would give it being equal to 4A squared, which would imply that the energy in the standing wave is 4 times the energy of the constituent waves. So looking at it in two different ways that otherwise seem valid, you get different answers. So one of them has to be wrong. And hopefully your intuition for physics has developed enough that usually energy conservation isn't the one that's wrong. Turns out that the second one is wrong, and it's because we made a faulty assumption. So the issue that we made, or the assumption that we made, is that the energy in a standing wave is just related to just the square of the amplitude. But remember where that formula came from. That formula came from realizing that the energy in a single oscillating particle has amplitude, or has energy proportional to the amplitude squared. And then we just add up the energies of all of the particles, and each of those particles has amplitude A squared, or has amplitude A. But the important point here is that, unlike a normal wave, a standing wave, or in a standing wave, each particle does not travel the same distance. When I say particle, I mean like the constituent of the medium that moves, or like of the sound that oscillates or whatever. It's just the thing that does the waving. And so that is, in a standing wave, each particle does not necessarily, or not even not necessarily, it just does not have the same magnitude of oscillation, or amplitude of oscillation rather. And just visualizing what a standing wave does, think about the point that's right in the middle, the node. Well, the particle that's there isn't moving at all. It's not oscillating up and down at all. And the particle that's here is only oscillating up and down a little bit. But the particle that's here oscillates up and down a lot. So we can't just add up the oscillation, or we can't just find the energy of a single one, write it in terms of its amplitude, and then multiply it basically by the total number of particles, because only 2 particles have that oscillation. The rest have oscillations that are smaller. So we have to account for that somehow. And the way that we do that is we have to integrate, just as we did before, we integrate the energy of each particle to compute the total energy. We need to write down the energy of a single particle in terms of its amplitude, which will depend on its position. And then we can use that to find the total energy. So remember from Monday, I think it was Monday, that the energy in a I thought I read, no, okay. So let me back up. So Wednesday, we wrote down a formula for we wrote down a formula that tells us what the disturbance is at any given point in space and time for a standing wave. And that was just, it was a product of signs. So the quote unquote wave function describing a standing wave was 2a times sine of 2 pi lambda over, or 2 pi x over lambda times sine of 2 pi, let me write it this way, 2 pi t over t. And so the oscillation of a particle at a given position, well, we don't care about the sign because that's just going to tell us that at one point it's at 0, but at one point in time it's at 0, at another point it's at its maximum, at another point it's 0, at another point it's at its minimum. We just want to know how far does each particle go. And so that's determined by these leading terms. Given a position x, this quantity that I put in a box, that tells us the maximum amount that particle will displace. So we can write the amplitude as a function of x, and use lowercase a to write the amplitude as a function of x, is just 2 times a times the sine of 2 pi x over lambda. And so this really is a position changing amplitude, and it's not constant, unlike for a normal everyday traveling wave. The amplitude changes with position. So from lecture 1, we gave a formula for the energy of a single particle given its amplitude. The energy of the single particle, this is for a wave on a string, of course, is 1/2 times omega squared. By the way, remember, omega is 2 pi f. It's the angular frequency. Times the amplitude squared, here I'm going to write it as a of x squared, times the linear mass density times dx, the width of the piece of string. And so we can integrate to get the total energy of the standing wave. The energy of the standing wave is an integral. Well, the position x goes from 0 to lambda, because this is one wavelength. And then we have to just do this integral. 1/2 omega squared, 2a sine of 2 pi x over lambda, squared mu dx. Now, it's a messy integral to do. It requires a substitution, and you can look at the answer in a table. But the end result is that you get that the energy in the standing wave is mu lambda omega squared a squared. Okay. Now, just as a reminder, the energy in a single traveling wave with amplitude a, or the energy in a single wavelength of a single traveling wave of amplitude a, is 1/2 mu lambda omega squared a squared. So the end result is that the energy in the standing wave is twice the energy in the traveling wave, which agrees with our energy conservation argument, which is a good thing because energy conservation is rarely wrong. So the mistake that we made when we just said, oh, well, the amplitude is, or the energy goes as the amplitude squared, is that that's only true so long as, well, okay, no, let me rephrase. The energy does go as the amplitude squared, but that constant of proportionality changes depending on the type of wave. So for a standing wave, that constant of proportionality is smaller than it is for a traveling wave. And so really that constant of proportionality is half as big. And you can work that out for yourself by doing this type of integral. So that's going to put an end to standing waves and waves in string mostly. We're going to move on to, we're still talking about waves, but we're going to talk about sound. Sound is a type of wave. So this is the beginning of chapter 2. So let's talk about sound. Begin at chapter 2.1. So first we need to answer a relatively straightforward question, which is what is sound? So sound is a type of wave, as I said. By the way, it's very hard to write different words from what you're saying, so bear with me. So it's a longitudinal wave. So remember what we talked about on the first lecture. There were transverse waves. These are waves where the disturbance is perpendicular to the wave. So if the wave's traveling, say, this way, then the thing that's oscillating is going this way, or maybe it's going this way, but it's certainly not going back and forth. A sound wave, a longitudinal wave, is a wave where the wave is traveling this way, but also you have little things oscillating back and forth. Maybe it's particles, maybe it's the change in air pressure is changing in that direction, whatever. The point is that the oscillation, the disturbance, propagates in the same direction as the wave itself propagates in. Now, this is a longitudinal wave that generally is understood not in terms of displacement, like a wave on a string, but in terms of compressions and rarefactions. So rarefactions are just the opposite of compressions. Compressions are areas of high density. Rarefactions are areas of low density. However, you could alternatively view the compressions and rarefactions as, well, no, it is just when the air molecules are close together, and rarefactions are when the air molecules are far apart. So sound waves can travel through really any medium, or rather any matter. I suppose you could come up with like abstract notions of a medium, but typically we use air because that's what we exist in. But like you can have sound traveling through water. I mean, that was traveling through air, but if my ear was in the water, type yes. Okay, no, we're good. Chat's awfully quiet right now. It's very strange. Oh boy. Okay, well. Yeah, chat's very quiet right now. Like nobody's typing anything. I hope. Like, are you guys here? Can you guys type things?
People are typing in the chat right now. I don't know if you can see it.
No, I can't. My chat's not responding actually, so I can't.
They're just saying that you froze and your camera is frozen at the moment, but we can hear you right now.
Okay. I'm going to turn off my camera temporarily. Oh boy. Oh, I hate when this happens. I have technical issues. So you can hear me and hopefully you can see the text or see what I'm writing. And when it unfreezes, maybe I will end the video. Right, so we were talking about what sound is. So the way that we perceive sound is by our sense of hearing. And so the thing that we actually detect is the pressure changes which cause the eardrum to vibrate.
Professor, we can't see your screen. Like your screen is freezing up too.
Close out of Chrome. I was going to show you a GIF, but maybe not. Right, the pressure changes cause the eardrum to vibrate. And then we have little sensors, little cells in our ear that detect motion, and that motion is translated into signals that go to your brain. So So that's what sound is. But we can go deeper. We can talk about what sound is like from a math and physics perspective, and that's by describing the displacement. So the displacement. Oh, okay. So I'm going to turn off my video. No, it's not even letting me do that. Okay. The displacement associated with sound, and I'm putting displacement in quotes here because it's not really a displacement, or it doesn't have to be. What is the actual thing that's doing the oscillating? This is so frustrating. Well, there's two ways that we can describe the displacement of a sound wave. There's the average particle distance from the mean distance, and particle, when I say particle, I mean like particle of air. Particle distance from mean position. So if a given particle of air on average is located at one place, when the sound wave passes, that distance will be on average some other distance, and that distance will be oscillating back and forth. Or, and perhaps more usefully, we can measure it in, or we can measure the disturbance or the displacement in terms of the local pressure difference from one atmosphere. I'm going to abbreviate one atmosphere as 1 ATM. That's the standard abbreviation. So like as the wave passes by, the particles, the atoms, the molecules in the air get closer and farther apart, and that changes the pressure of the air. I still can't see chat, so and whenever I click on Zoom, it crashes. Oh boy. So I'm going to not touch it, which means that I can't answer questions, which is unfortunate, but I don't want it to crash. So I hate when this happens. I'm sorry, guys. Maybe I need to get a new tablet sooner than I thought. But anyway, like I was saying, the describing the displacement or the disturbance in terms of a local pressure difference is a little bit more useful, because then you don't have to do statistical averages. Pressure is just a thing that you can measure, and you don't have to like get out a microscope and look at where the molecules are and so on. So I really wanted to show you a GIF. I'm gonna venture a guess and say that I won't be able to. Yeah, okay. So I'm not gonna be able to. So, but it is linked in the lecture notes. Basically, I was gonna show you a GIF of, it was kind of like the GIF that I showed you when we were talking about longitudinal waves in the first place. It involved like the pressure waves moving, and then there was a highlighted little red dot that showed an atom moving, and it was moving back and forth. Anyway, I can't show you that because my tablet will crash if I do. So instead, I am going to proceed. So let's talk about, or you know what, maybe I'll draw a picture. So if you have a wave traveling, yep.
Can you hear us?
Yeah, I can hear you.
Someone's asking if it's okay to ask questions on Discord. If you can see, I'm there.
Yeah, that's actually a good idea. Yeah, feel free to
Okay.
ask questions in Discord.
All right, thank you.
You're welcome. Right, so the picture, so like in a sound wave, it'll look something like this. And then there'll be like a few, you know, it's less dense here. And so the sound wave travels through. And so the thing is that these areas of high pressure and the areas of low pressure do not occur when a particle is at its maximum distance from equilibrium. In fact, these areas of maximum pressure occur when a particle is at its average position. And the areas of minimum pressure also occur when a particle is at its average position. The particle is moving fastest when it's halfway between, or rather it's displaced the most when it's halfway between a maximum and a minimum, which is just to say that the oscillation, the particle motion, compared to the pressure, well, the waves actually look different. They're not in phase with each other, i.e. when one's at a maximum, the other is not. In fact, they're actually exactly out of phase. This is to say the maximum displacement away from its average position occurs when the pressure is at equilibrium, and vice versa. So this just implies that the displacement is 2 pi radians out of phase from the pressure wave. Sorry, not 2 pi, it's pi over 2 radians out of phase. Now this is a strange phenomenon, but the reason why this happens is because when you have a pressure differential, it creates a restoring force. And as you guys probably know from 9A, a force doesn't necessarily cause maximal movement immediately. It takes time for the force to cause that motion. And so by the time the pressure has been applied to cause that change in displacement, the pressure has already changed back to where it was. So you get this kind of oscillating up and down. So just as a picture, or just to show you what a picture might look like, if we were to plot, say, pressure with displacement, it would look something like this. So we have our pressure wave. So we might have maximum pressure at this position where we have minimal displacement, whereas we have maximum displacement. Oh, this is a terrible drawing, I'm sorry. There we go. So the oscillations are just not in phase with each other. This is all I'm trying to get at. Now, it doesn't really matter. By the way, where are people asking on Discord? Nobody's asked any questions yet. Okay, so this isn't super relevant, but it does explain why. It does explain what we're about to talk, or it does explain the properties of sound waves or standing waves in sound that we will talk about in a bit. So let's talk a little bit about the properties of sound waves. We talked about the properties of waves on a string. For example, we talked about the wave speed on a string. It was related to the tension and to the density of the string. So we can do the same for sound waves. Now these we won't derive. I mean, they weren't even derived in the LibreText because they're just complicated to get. But I mean, I can at least give you what we've empirically measured. So the sound wave velocity in air at standard pressure and temperature, standard temperature and pressure, that's STP, is 344 meters per second-ish. But just like everything else, just like in a rope or a string, the wave speed depends on the medium. So for fluids, and gases are included in this description of fluids, gases are fluids, the speed of sound is the square root of b divided by rho. Now b is something called the bulk modulus. Basically says how sticky the material is to itself, and it kind of behaves like tension. And rho is the density of the medium, just like linear mass density. Similarly, for solids, so there's only 2 types of matter that we experience regularly. Those are fluids and solids. Fluids include gases and liquids. It has a very similar formula. It's just y divided by rho. In this case, y is something called the Young's modulus, which basically says how springy are the bonds between atoms in the material. And rho is, again, the density of the medium. So hopefully you guys can see the parallels between a sound wave speed and the wave on a string. The wave speed on a string was the force of tension divided by the density, the linear mass density in this case, because it's a one-dimensional wave. So, I mean, the relationship here should be pretty clear. A sound wave is very, very similar to a wave on a string. We've just replaced the tension with the appropriate, similarly like springiness, stretchiness, stickiness of the material property that the wave's traveling through, and we've replaced the one-dimensional density mu with the three-dimensional density rho. But I mean, otherwise, like the formula is roughly the same, and so that should kind of indicate to you that there's something universal happening here. And then similarly, we can also compute the intensity for a sound wave. Again, not using the tools that we've already developed, but in principle, it's doable. The intensity of a sound wave is 1/2 times the square root of rho b. Remember what the intensity for a string was. I'll show you what it looks like in a minute. Times omega squared, angular frequency, times the magnitude of the displacement or sorry, the amplitude of the displacement wave. But this can be written in terms of the amplitude of the pressure wave as well. which would write it as a squared the amplitude of the pressure wave, because you can always describe a sound wave as either a pressure wave or a displacement wave, and they're just different ways of representing the same thing, divided by 2 times rho b. So this is just a formula for the intensity of a pressure of a sound wave, or of a sound wave, written in terms of its displacement amplitude or its pressure amplitude. Now, just as a quick reminder, the intensity on a string was 1/2 square root mu f omega squared a squared, which looks an awful lot like the intensity of a sound wave written in terms of its displacement wave. Mu is replaced with rho, b is replaced with f, as in the velocity, and then everything else is the same. So again, there's something big happening here. That is that like all of these wave properties, they're all descriptions of like some underlying universal property or type of phenomena that occurs in nature, and that's why these things are related. That's why a wave on a string is still a wave, just like how a wave in the air is still a wave. They're both waves. They both have these same properties. They just depend on different material quantities. But the important part is that both of these are proportional to proportional to the amplitude squared. That's an important, and which just confirms what we suspected last time, that the energy, or rather the intensity of a wave, regardless of where it is or the medium or what type of wave it is, the intensity is proportional to the square of the amplitude. Now, we don't hear, like the way that we perceive hearing or that we perceive sound is not by measuring intensity. Does sound wave travel at 344 meters per second strictly in air? And if so, what's the case formula for finding velocity in other gases? So this 344 meters per second can be found by plugging in the appropriate numbers into the formula in fluids. Fluids are, or gases are fluids. So you just have to find the bulk modulus of air and the density of air, and that'll plug those both in, and it'll give you 344 meters per second. If you had a different gas, you would find the bulk modulus of that gas, you would find the density of that gas, and you'd get a different wave speed. Right, so like I was saying, we don't perceive by like directly measuring intensity. And the reason for that is that like a jet engine is clearly like millions of times more intense than like a cricket, right? But like a jet engine only sounds like maybe 50 times louder or 100 times louder or whatever. Like our perception is not linear with intensity. So we came up with another system of measurement, which is called the decibel, or the decibel. And we can relate, not intensity, we can relate the intensity to a decibel rating. Now, decibel is technically just a logarithmic measure of intensity, but it's useful because we don't hear linearly, we hear logarithmically. So just as a reminder, not a reminder, a note, the minimum intensity for us to be able to hear it, like you could go out and measure, like if such and such an intensity hits your ear of sound, what's the minimum amount before you just wouldn't hear it, before it'd be too quiet? Now, remember, intensity is power per unit, or for three-dimensional waves anyway, it's power divided by 2 pi r squared, so it's power per meter squared. So this is what we call I naught. It's the reference intensity, and it is roughly 10 to the minus 12 watts, units of power, divided by an area, meters squared. Now, we can also figure out, well, okay, that's a good reference intensity, because that's like the quietest thing that humans can hear on average. That you can also measure, well, how much intensity would you need before the sound was so loud that it started to hurt? Like you're really, really close up to a speaker at a rock concert, or you're next to a jet engine or whatever. So what's the threshold for pain? So the threshold for pain, maybe we call it I sub pain, is about 1 watt per square meter. And so anything between these will just be a sound. What happened in W in the intensity formula? Oh, yeah. So the frequency of the pressure wave, I don't think I may have copied my notes wrong, but the pressure wave frequency shouldn't matter. At least that's what I have. But let me double check. That's a good question. I think it should be there, honestly, but I could just be wrong. Let me double check. Yeah, no, it's just not there. Which is strange, but that just says that the intensity doesn't depend on how quick the wave is oscillating. It just depends on how big the oscillation is. It just is what it is, right? And you can relate the amplitude of, and the reason for this, by the way, is because in a string, like in a wave on a string, the amount that the string can vibrate up and down depends on how quickly the string is actually vibrating. But so when it comes to displacement, the frequency, basically the amplitude of the displacement is related to the frequency. If the frequency is higher, the displacement will be bigger. These formulas I gave you. Deriving them is challenging, so I gave them to you. The point is that if you view the sound wave in terms of a pressure wave, well, now the amount that the pressure changes by doesn't depend on the actual, doesn't depend on how quickly the pressure is changing. It only depends on how much the pressure is changing by. Whereas for a displacement, in order to get that displacement, that displacement is related to how quickly the atoms are moving back and forth, because if they're moving faster, then they'll displace more, basically. Right, so the threshold for pain is about 1 watt per square meter. And the point is anything between these intensities is something that we can hear that like won't cause damage and is hearable, is audible. So like we can hear and experience sound over a 12 order of magnitude range. And so if we just heard in terms of, like if you hear a cricket chirping, it's not a billion times quieter than a jet engine, right? It's like 1,000 maybe, or something like that, but it's not a billion because we can't perceive that big of a difference. So in order to handle this, it's because it makes our eardrums start to move too much. In order to handle this, our ears have evolved basically to hear via a logarithmic scale. So what we do in order for a logarithmic scale to make sense is we need to have some sort of reference intensity. Now what we're about to do wasn't decided by nature. This is something that we came up with, but it's a useful way of characterizing what we experience. So we use the minimum intensity for hearing as a reference intensity. And then we say, okay, well, how much, like what is the logarithm of the ratios between the reference intensity and whatever we're hearing? i.e., we write beta, which is the number of decibels, as 10 decibels, which is a unit, times the logarithm, base 10, of the intensity that we're hearing divided by the reference intensity. So this is the decibel measure of the intensity that we're hearing. So for example, if you are hearing something that, if the intensity that is impinging on your ear has magnitude 10 to the minus 12 watts per square meter, i.e. it's equal to the minimum intensity for hearing, then you would evaluate this. You would get the 10 decibels times the log base 10 of 1, because I naught over I naught is 1. So log base 10 of 1 is 0. So that would have a volume of 0 decibels. On the other hand, if instead you experienced an intensity of 10 to the minus 11 watts per square meter, then you would have 10 to the minus 11 divided by 10 to the minus 12, which would just be 10. So you have log base 10 of 10, which is 1. And then you multiply it by 10 decibels. So something that has that intensity would have a volume of 10 decibels. And so let me just give some examples of calculations. So like I already said, 0 decibels. This implies that the intensity is 10 to the minus 12 watts per square meter. 120 decibels implies that we are at the threshold for pain, which is 1 watt per square meter. Now we could go higher in principle, right? So it turns out that 278 or approximately 278 decibels, this would be something like the intensity is 6.3 times 10 to the minus 15th watts per square meter. It's a lot. This is about the sound wave, or really it's a shock wave at this point. This is the shock wave intensity of a nuclear bomb. And really, so you're at this point, It's not even the nuclear bomb that kills you. Well, it is. You'd be vaporized before this happened. But if you could somehow hear this without being vaporized, you would be dead from the sound. It's just so much energy on your body, you would just turn into salsa, basically. If you play any tabletop games, like tabletop RPGs, this is what might be called the chunky salsa rule, because there's so much energy just being applied to you at every point in your body that you would just turn to mush. Very, very unpleasant, presumably. But the point is it's only like twice the decibels, roughly twice the decibels of the point of the threshold for pain. But it's 15 orders of magnitude, 1 trillion times more intense. So, you know, this decibel scale can vary over such a wide range of energies. So just as a reminder, the intensity goes as amplitude squared, but also the intensity goes as 1 over r squared. So that is to say, if you, and this is because this is in 3 dimensions, of course. If you say double the base, like the intensity at your source, but also double the distance, then the intensity that you'd observe would be the same thing, or would be the same. And so it would sound the same volume. That is, if A doubles, and this is the amplitude at the source, and R doubles, then I stays the same. Now, why is this useful? Well, you could imagine if you want to hear someone that is twice as far away, you have to produce a sound wave that is twice the amplitude. And there you go. Bada bing, bada boom, right? So this just tells us how amplitude and intensity and distance all relate to each other in 3 dimensions. And we've kind of already touched on this in the first lecture, so this is more of a recap. So that's how we characterize energy and amplitude and intensity, all of these things of a sound wave. We use the decibel system. And by the way, you can use decibels for anything that is measured in intensity. It's just decibels is useful for sound because it turns out we perceive sound logarithmically. So it's a useful measurement. I mean, we also technically perceive light logarithmically. So you could use decibel to measure the brightness, but we use a different system for that. We use something called candela, I think. I think it's called candela. Right. So, okay, so that touches on the energy associated with sound waves and intensity and volume, hearing. So now we can just start doing more, because so far all we've talked about is describing phenomena where you just have one source of a sound wave and that's it. Nothing's moving, nothing's happening. You're just some distance away from a sound wave. You can figure out the intensity, you can figure out the amplitude, all of these things. You can figure out how loud it sounds and so on. But sound does, like, a lot more things happen. For example, what would be a good example? Dolphins use echolocation. I mean, so do bats. Clearly, they're using sound somehow to figure out A, how far away things are, and maybe if they're smart enough, B, how fast they're moving. So let's talk about what happens when the 2 parties involved in a sound wave, the source of the sound wave and the receiver of the sound wave, are both moving. So that takes us through to section 2.2. Oh my God, I can see your text. Maybe that's from a long time ago. So we're going to talk about the Doppler effect, which precisely describes what I just talked about. This is section 2.2. So, like I said, waves in general are produced at a source and are detected or measured at a receiver, or in the case of sound, we might call that receiver a listener. So the question then you might have, and you know, it would be a reasonable question, is, I mean, sound is traveling through air. It's moving at a certain speed. So what happens if, what happens to what the receiver observes or detects if the receiver is moving, or if the source is moving? Like does anything change? Does the receiver just receive the same wave? Like, is nothing changed, or does something change? It's a reasonable question to ask, and we know from evolutionary things that indeed something does change because echolocation exists. And so let's talk about the types of, or the characteristics of a sound wave. So the characteristics of a sound wave that we care about, obviously the amplitude changes when things are moving because the distance is changing. But disregarding amplitude, what else describes a sound wave? Well, the frequency of a sound wave describes a sound wave, right? And the frequency is measured by the receiver as the number of pulses per second. So you can think of sound waves as having like a pulse at each of their peaks, right? And so the number of pulses that pass by you per second, that would be the frequency. 5 per second, 100 per second, whatever. The wavelength, well, that's just take a picture of the air molecules, and the wavelength is just the distance. So this is independent of any motion. The wavelength is just what it is. It's just measured with a ruler, say. It doesn't depend, it's not something that the receiver determines based off of their situation. It's just a thing. You just sit in the air and you just measure the distance between peaks. And then wave speed. Wave speed is also something that affects wave propagation. And so the wave speed can be determined by the receiver or the source by applying the always true phenomenon that the wave speed v is equal to lambda f. So in the case of the receiver is receiving some amount of pulses per second. They can measure the wavelength, and then they just multiply them to get the wave speed. So let's consider some cases. So yeah, we will get to sonar. Sonar is pretty cool. So let's consider the simplest case, perhaps the simplest case. I mean, well, really the simplest case is neither are moving. And then whatever, if the source spits out 5 pulses per second, the receiver will receive 5 pulses per second. They'll both measure the same wavelength. They'll both measure the same wave speed. Things start getting complicated when things start moving relative to each other, because, you know, like you can think of like sonic booms, right? Sonic booms occur because the thing creating the sound wave is moving so fast that the sound waves can't travel in front of it. The sound waves aren't moving fast enough to overcome. So you end up with like an accumulation of waves at the front of the object, and which produces a sonic boom. So we're going to consider, I think that, no, okay, still not working. Yeah, still not working. Okay. So we're going to consider when the case when a stationary receiver observes sound from a moving source. So I'm going to draw a picture. So here we have our source. Call it S. It's moving at, say, speed v sub s to the left. And then we have our receiver, say, over here. Receiver is not moving at all. So what the sound waves are going to look like is, well, the first sound wave was emitted, say, back here. So it would have traveled the furthest. So maybe it has a wavefront. Let me fix this drawing a little bit. Let me put this a little bit closer. So the first wavefront may have been emitted, say, here. And so notably, it's not centered on the source anymore, because the source has moved in the time that the wave has traveled. And then the next one might be, say, here. Again, it's still not centered, but it's closer. The next one might be here, which is closer to the center because it was emitted more recently, and so on. And so in this case, the source still emits a pulse. Like if they looked on their watch, they would emit a pulse every t sub s seconds. T sub s being the period observed by the period used by the source. However, the point is, so the source emits every t sub s seconds, but in the time that it takes for it to emit its next pulse, the receiver will have moved a little bit, or the source will have moved a little bit. And so, so each wave is emitted a little bit closer to the receiver. And so you have this, so the sound waves appear to arrive sooner than what they otherwise may have. And the reason for this is, note that the wave fronts themselves, v, they just move at whatever speed. Like the wave fronts, like the air isn't moving, the air or the wave, the sound waves are just moving at the speed of sound. Always, they just are just moving at the speed of sound. And so in the time between pulses, the source has moved, well, they've moved their speed times the duration. V sub s times t sub s. They've moved that distance, units of distance. And so their next pulse will have a head start. And so, like I said, the waves themselves aren't changing speed. So the first pulse, the previous pulse, has moved, well, it's moving at speed v, the speed of sound, times the distance, or times the duration. That's to figure out how far. So it has moved v times t sub s units of distance in that time, in the time between pulses. So the distance between pulses, well, the first pulse moved v times t sub s. The next pulse was released after the source has traveled v sub s times t sub s. So the distance between pulses, which is also known as the wavelength, is lambda wavelength, which is v times t sub s, that's the distance the previous pulse traveled, minus the distance that the source traveled, because the source kind of gave the second pulse a little bit of a head start. So we can factor this to be v minus v sub s times t sub s, and then we can write t sub s. Remember, the period of oscillation is the inverse of the frequency. So this is v times v sub s, or sorry, v minus v sub s, divided by the frequency that the source emits at. Now, the question then is what does the receiver detect? The receiver detects that wavelength and still measures, and the waves are still traveling at the speed of sound. And so we can use the relationship between frequency, wavelength, and speed of sound to figure out what frequency the receiver detects. This f sub r is the frequency detected by the receiver. And so we can solve, we get that f sub r is equal to v over lambda. Now we already know what lambda is. We know what the wavelength is. The distance, we know the distance between waves that of this wavefront. And so this, plugging in our result above, this is just equal to v divided by v minus v sub s over f sub s, which is rewritten, it's f sub r equals v minus v sub s times f sub s. So this is to say, the frequency detected by the receiver when the source is moving towards the receiver changes. They hear a higher pitched sound. By the way, I should be clear. Like if you hear a pitch that's higher, like a higher pitched sound, is a sound wave that is a higher frequency. So when the source is moving towards the receiver, the sound that they hear is higher pitched because the frequency, the rate at which these wavefronts are hitting their ears, is faster in the distance between pulses. Yeah. Yep, you're right. Sorry, right there. And so, for example, if the so as v sub s gets bigger, as the speed of the source gets faster, the frequency goes up even higher because v divided by a number smaller than v minus v sub s is smaller than v. gets bigger. It's just a multiple. And you can even tell that when the source starts moving towards the listener at the speed of sound, the frequency goes up to infinity. And that just says that this calculation breaks down. And this forms a sonic boom, actually. Right. So we can do the same thing. Oops. If the source is moving away from the receiver, well, then the distance between wave pulses is bigger because it's kind of the source is kind of handicapping the waves on their way to the receiver because they're starting out further away. So the result there is that the observed wavelength lambda is v plus v sub s over f sub s, and so the frequency that the observer or that the receiver receives is v divided by v plus v sub s times f sub s, which is just to say, as the speed of the person moving away from the source moving away from the receiver increases, the frequency goes down. So something traveling away from you will have a deeper sound, less high pitched. And so we can actually just combine these into a single equation just to kind of capture both phenomena. And so the way we write this is we write that f sub r is equal to v divided by v minus plus v sub s times f sub s, frequency of the source. And so this formula here, this is the frequency, or this formula is applicable when the source is moving directly toward or directly away from the receiver. And then you just have to pick the minus or plus correctly. And so the general rule of thumb here is we pick the top sign, so in this case, the minus sign, when the source is moving towards the receiver. And we'll see why this convention is chosen earlier. Now, just as a quick note, the result that we get here changes significantly if the direction of motion is not head-on. And the reason for this is because we don't really care about perpendicular motion. We only care about motion in the same direction as the line between the source and the receiver. And so you'll get a trigonometric function of the angle that's involved here if the source is moving like off at an angle. But that's kind of beyond the scope of this class. I am going to ask you guys something about this on the homework, but I'm only going to ask you about it conceptually. I'm not going to ask you to derive it. Okay, now let's do the same thing, but this time the source is stationary, but the receiver is moving. Consider a stationary source. You might think that the formula is the same, but it's not. It's similar, but it is different, which is kind of baffling. So in this scenario, so here we have our source, S, and it's just staying put. So the distance between, so it's not like lopsided or anything at all. At least I tried to draw it not lopsided. The waves are still moving forward at a speed v, but the source is not moving. But now the receiver, r, is moving towards the source at a speed v sub r. So in this scenario, both the source and the receiver agree on the distance between pulses. I mean, just like before, they both agree on the distance between pulses because you can just get a ruler and measure them. But the receiver observes the pulses hitting it more quickly than the wave speed, right? So how do I want to phrase this? So the receiver knows how fast the wave speed is. The receiver also knows that given a wavelength, it should be encountering these pulses at a certain rate. But because the receiver is moving towards them, it's catching up to these waves. The waves don't have to travel as far to get to the receiver. And so it observes the pulses hitting the receiver more quickly than what they would do if they were traveling at the wave speed, i.e. basically the wave speed has increased, the wave speed relative to the receiver. So from the receiver's perspective, the pulses are moving towards it. At a speed of, well, this is a relative speed calculation. So it's just the sum because they're moving towards each other at a speed of v plus v sub r. That's how fast the pulses are moving towards the receiver. Now, because the distance between the pulses is just lambda, because the measured distance is lambda, measured wavelength, the frequency detected by the receiver is just related to it's v plus or v equals lambda f. The receiver can compute, or the receiver determines the frequency by, well, the wave speed that the receiver detects is v plus vr, and that should be equal to lambda times f sub r. It's the frequency that the receiver sees. And so the frequency that the receiver sees is v plus vr divided by lambda, which is, but lambda is also equal to the regular wave speed, this is from the source's perspective, divided by the frequency at the source. So the frequency observed by the receiver is v plus vr divided by v times v, or f sub s, the frequency of the source. And so we can do the same calculation just as before, in this case with the receiver moving away from the source. And we find that the frequency that the receiver observes is v plus or minus v sub r divided by v times f sub s, where here, this formula is applicable when the receiver moves directly towards or away. Away from the source, but the source is stationary. And so again, using the same convention, the top sign, in this case, the top sign is the plus sign, is when when the receiver is moving toward the source. The direction of motion matters here. And so we can actually just combine them when they're both moving. Both S and R are moving. Well, the end result is the combination of these two. We get that f sub r, the observed frequency by the receiver, is v plus or minus v sub r divided by v minus plus v sub s times f sub s. And so here, this is our final Doppler effect equation. This is the Doppler effect, by the way. The Doppler effect is what happens, is I can't believe I didn't say this. The Doppler effect is the observed change in frequency when a source and a receiver are moving relative to each other. So here, the top signs correspond to that object moving towards the other. So for example, if say if the receiver is to the left of the source, so if we have a receiver here and we have our source over here, if the receiver is moving this way and the source is moving this way, well, the receiver is moving towards the source, so we would use the positive sign here. So we'd have plus v sub r, and the source is moving away from the receiver, so we would have plus we would choose the bottom sign, which would be a plus v sub s. So we would get in this case that f sub r is equal to v plus v sub r divided by v plus v sub s, f sub s. On the other hand, if they were both moving towards each other, like this, say, then they're both moving towards each other. So we choose the top sign in both cases. So we choose the top sign for the receiver, so it's plus v sub r. We choose the top sign for the source, which is minus v sub r, or v sub s. And so the frequency of the receiver would be v plus v sub r divided by v minus v sub s times the frequency of the source. That's how you do this. And so in general, an easy way to remember this is if the distance between the objects, the source and the receiver, is shrinking over time, then the frequency that the receiver detects should be higher pitched. It should be the ratio of these velocities should be greater than 1. And if the distance is growing with time, then the frequency, then the ratio, the frequency should go down. So the ratio should be between 0 and 1. There's a handy table that I linked to in the lecture notes, so you can see those when I post them. And you know, there are a few examples that are littered throughout the lecture notes as well that you can take a look at in the Rice University textbook that will also be helpful. So I promised we would get to this, and it looks like we will, which is really cool. We're actually going to finish maybe even early. I didn't actually prepare more lecture notes than this, but we'll see. So I promised that this would be useful. So let's actually talk about an application here, which we very rarely do in this class because applications, I'm a theory guy. So let's talk about radar and echolocation. So when a wave reflects off of a medium change, and remember, waves reflect off of changes in medium. So like a sound wave will reflect off of the interface, off of like the ocean's surface or like a lake's surface, because the medium is changing and the wave speed changes accordingly. So when a wave reflects off of a medium, which it does, like when it bounces off of anything, like if there's a metal sheet, that's a different medium. It has a different speed of sound, and because sound can propagate through anything, there will be some transmitted and there will be some reflected. Anyway, when a wave reflects off of a medium change, the frequency is the same before and after the bounce, according to the object it bounced off of. So let me write that down. During a reflection, the incoming and outgoing frequencies are the same. Which is just to say, and I mean, that kind of makes sense. And the idea here is that like when one sound wave, like if you have a sound wave in air and it hits, I don't know, a steel block, right? The number of wavefronts that are hitting the steel block, that is the incoming frequency per second, the number of wavefronts per second that are hitting the steel block, that's the incoming frequency. Well, that means that the bits of the block the bits of the steel block are going to vibrate at that frequency. And so they will re-emit a sound wave at the frequency they're vibrating at, which is the frequency of the incoming sound wave. And so the reflected wave will have the same frequency that the thing it's reflecting off of observed the incoming wave to have. So this is useful because the thing that the wave is bouncing off of might be moving, or the thing that's sourcing the wave originally also might be moving. And so those frequencies that the reflecting object detects, in air quotes, that the detecting object experiences might be different from the frequency that the source emits at. So for example, we can imagine a source producing a sound. Let's do an example. Imagine a source producing a sound that bounces off an incoming object, moving at speed v0. So the picture here v naught or VO, the speed of the object. So the picture here is like you have like a speaker that's just sitting on the ground, and that speaker travels towards something, bounces off of that something, but that something is moving towards the speaker. Maybe it's like you have a speaker on the ground and you have like a truck driving towards the speaker. Well, the object, the truck in this case, is moving towards the speaker. And so from the object's perspective, the frequency of the wave will be different than what the source emitted at. So from the object's perspective, well, we can go consult our formula, but the object, in this case, playing the role of the receiver, will detect a frequency that corresponds to the Doppler effect when the source is stationary and the object is moving. The frequency is F sub O, the frequency detected by the object, be V plus V sub O divided by V times the frequency from the source, right? So the reflected wave will have a different frequency. And in this case, since it's moving towards the source, it'll have a higher frequency. But that wave is sourced from a moving object. The emitter of that wave, in this case, the truck or the object that's moving, the new reflected wave, and so when the receiver, when the reflected wave bounces back and it hits the original source, which maybe also has a microphone attached to it, like a radar or like a sonar dish, there will also be a Doppler effect applied there. So the original source, now playing the role of the receiver, will observe a different frequency. The received frequency at the location of the source, stationary of course, would be V over V minus V naught, because in this case, now we would use the formula for when the source is moving and it's moving towards the receiver. And this would be times the frequency of the emitting source, which is F naught. And so we can plug in our result for F naught. This is V over V minus V naught times V plus V naught over V times the original initial frequency from the source. And this tells us that the source, or the receiver, which was also the source, will detect back a frequency of V plus V naught over V minus V naught times the original source frequency. And so if the receiver knows the frequency that it emitted at, say the first time, maybe it's emitting at 1,000 hertz, maybe it emits 1,000 pulses per second. And it knows it can measure the frequency that it receives the wave at from the echo, from the bounce. Well, then we can, and assuming it knows the speed of sound in the area that it's in, which it does, it's like 344 meters per second or whatever, then the source / receiver can just calculate how fast the thing is moving towards it or how fast it's moving away from it. And so you can actually learn how fast something is moving just by bouncing sound waves off of it. This is how, like echolocation works. Well, okay, it's not quite how echolocation works. There's one more thing that you can learn. You also know that these waves travel at a fixed speed, right? Travel at 344 meters per second in air, or some other speed in water, some really fast speed. So you can also time how long it takes between when you send out the pulse and when you receive the pulse, right? And so that time difference will tell you how far away it is, because the wave is traveling at some fixed speed. Just divide the time, or you just multiply the speed by the time. And the Doppler effect, this calculation of measuring frequencies, will tell you how fast it's moving. So you can learn a lot about an object just by sending waves at it and then listening in air quotes, for the reflection, for the echo. Now, this is really how echolocation works. The dolphins or the bats or whatever will send out pulses. and then it'll they have built-in organs that can do this calculation for them, and then they will use their ears to and they will compare the time when their ears receive their reflections with the time when they sent out the clicks, and then they can use that to figure out how far away things are. So this will tell them what their surroundings look like, what their environment looks like, because they can figure out, well, directly ahead of me, there's something 5 meters. Directly to the right, there's something 50 meters. So maybe there's a wall in front of me and there's a big area over to the right. And so they can use that to basically see using sound. And not only that, and I don't actually know if dolphins or bats do this, but they can also figure out how fast something is moving, but just by the change in pitch. I suspect they don't do that because that seems a little bit too advanced, but we can do that certainly. And while we don't do this with sonar, we do this with radar. Now, radar is very, very similar. In this case, it's a light wave. It's a radio frequency light wave. So it's a very long wavelength wave produced by a radio antenna or a radar dish. Those light waves are sent out in pulses with, and there's a whole science behind getting the spectrum and getting the frequency and all of that and the shape of the waves correct. But they send out these waves. They can figure out how far away something is. They can figure out how fast it's moving. And so if you send out these pulses and you send them out in straight lines and you rotate, that's when you get this boop, boop, boop thing happening, right? The beep, 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 the radar thing from the old timey 1960s, whatever. So this line indicates the direction that the wave was sent out. And so when it encounters an object, when that wave encounters an object and bounces off of that object, the wave bounces off, comes back, and they can A, tell how far away that object was by the timing, and B, they can tell how fast it's moving, whether it's moving towards or away. They can also figure out, using more complicated techniques, whether it's moving left or right. And then you just sweep around. You turn your radar in a circle. And so every time your thing sweeps, this is why it's called a radar sweep, when your wave makes a full 360-degree arc, you've covered everywhere. And so now you know where everything is. Now, things get a little bit tricky with light because light doesn't have the same Doppler effect as sound does. It has a very closely related Doppler effect, but light is a little bit different. Light doesn't travel in a medium. And so there's not like a reference medium that you can use to figure out the wavelength. So for air, for sound waves in air, you just go into the reference frame of the air itself, the air where the air is stationary, and then you just measure wavelength, and that's just the wavelength. But there's no such thing that you can do with light because light travels without a medium. And also, on top of that, the observed speed is always the same. So in the case when the source was moving, sorry, when the receiver was moving relative to the source, or when the receiver was moving relative to the air, the receiver, it seemed like the receiver was seeing faster sound waves. The sound wave was faster. This doesn't happen for light. For light, everybody always sees the speed of light moving at the same rate. It's moving at 3 × 10⁸ meters per second. So we call the speed of light c. C stands for constant or something along those lines. So everybody sees the light moving at the same speed. So the derivation of the Doppler effect is a little bit different. And you have to take into account special relativistic effects, which changes things. But the end result is that the frequency that the receiver detects is related by a different factor, but it's similar. It's c plus or minus v.
Sam, I don't think you finished your definition for like observed speed is always the same.
One more time.
People are asking about what's after speed because you just said speed is always and then
period. Always the same. Yep, you're right. Well, actually, it's always c, and c is the speed, which is you know what? I'll just put this in. I'll just actually write it out. It's c is equal to 3 × 10⁸ meters per second. This is in a vacuum. In air, it's slightly slower, but it's still always fixed. Is the observed speed of light, speed for light always the same because it's massless? Yeah, basically. That's basically why it's always the same. Anyway, so the formula for the Doppler effect for light is c plus or minus v divided by c minus plus v times the source frequency. And again, we choose both top signs. The top sign is when the two objects are moving closer. And the bottom sign is when the two objects are moving away. And so we choose them in sync. So if the two objects are moving closer, you choose the top sign in both cases. When the two objects are moving further away from each other, you choose the bottom sign in both cases. And then the v is the relative speed of R and O, or R and S. So like, for example, if I'm traveling 5 meters to the right, and if I'm to the say, let me just draw a picture. So here's the receiver and here's the source, and we're both traveling 5 meters per second inward, then the V that we would plug in here to get the frequency that I observe, the frequency of light, it would be 10 meters per second. And because we're moving towards each other, the frequency would be c plus 10 meters per second divided by c minus 10 meters per second times the original frequency. Now, we haven't actually talked about how light oscillates. Light has frequency. It is a wave, just like sound, just like on a string. So on a string, the frequency is just how quickly does the string move up and down. For sound, it was how quickly does the pressure go from high pressure to low pressure and back. For light, it's something a little bit harder to explain, and we will talk about light in detail. But basically, it's something called the electromagnetic field. The magnitude of the electromagnetic field changes with time as a light wave passes, and that's the thing that's doing the oscillating. And the important point is that that frequency, the frequency at which the electromagnetic field is oscillating, affects the color that we see. So in particular, red colors, red light is a lower frequency than blue light, or it's a lower frequency than green light, and green light is lower frequency than blue light. So if I have my flashlight, if I have a red flashlight and I'm traveling towards you really quickly, you might see that red flashlight actually emitting blue light, because you will observe with your eyes a frequency that is higher, i.e. shorter wavelength, i.e. bluer light. The light will go from red to blue because I'm moving towards you. And you can figure out the change in frequency by using this formula. Now, keep in mind, the speed of sound is 344 meters per second in air. We can make planes that go Mach 3, right? So like we can experience, as humans, we can experience the full gamut of the sonic Doppler effect, right? Which is just to say, like we can see what happens like when things move really, really close to the speed of sound, we start to detect very, very strange phenomena. Like the frequency goes way up if something's moving towards you. The same can't be said about the speed of light. The speed of light is roughly 300,000 kilometers per second. Nothing we can make moves even close to that fast. The fastest thing, like objects that are orbiting the Earth, move something about 17 kilometers per second, not 300,000. So on an everyday level, you will experience the sonic Doppler effect. Like every time a car drives past you, you're experiencing the sonic Doppler effect because you hear, like it starts off low pitch, then it gets higher as it passes you, and then it gets low again. And so, sorry, no, technically it would actually just start off high and then get lower. So it's when a fast car drives by, it's that meow sound. So we experience that. Like we can detect that, we can hear the difference. You'll never see this with light. You'll never see this photonic, or I don't know what it would be called, the light Doppler effect, because things just don't move fast enough. If you're moving towards me at 10 meters per second, the speed of light is 300 million meters per second. Like the difference in frequency is going to be so minimal, we just can't We just can't observe it. No. So, and I didn't clarify this. Light, electromagnetic waves, includes radio waves. We just can't see them. But we can build radio dishes that can detect them, and we can still measure their frequency. We just can't see them with our eyes, but it's still light. Same with infrared light or infrared electromagnetic waves, like heat waves. That's light. It is just light. We just can't see it. Same with UV rays. That's light. Just can't see it. We can only see a narrow band of electromagnetic waves, and we will talk about this in more detail. We're actually going to talk about light pretty heavily, like next week. But right, so the point is we just can't experience this, so that's why it seems a little bit more strange to imagine like the color of something changing based off how fast it's moving. But it's the same phenomenon, just like when you hear a fast car driving by, the sound wave drops in pitch. It's the same phenomenon. It's just not part of our everyday experience. So this is so you could use the same sort of calculation to do radar, where you use radio waves. So the Doppler effect will still affect the radio waves. You shoot out your radio wave at an object, it bounces off, you detect it. You figure out how far away it is, because you know the speed of light and you know how long it took to get there and back. And B, you know how the frequency shifted, so you can figure out what direction it's moving in and how fast it's moving. So the Doppler effect is super useful. Like, in fact, funny story, and I know I'm rambling, but I don't have a whole lot more to go over anyway. When the British invented radar in the 1940s during World War II, not when they invented it, but when they managed to put it on planes, they wanted to keep that information top secret, because telling the Germans, telling the Axis forces that they have a way of seeing at night the fact that the Germans don't know that was a huge military advantage. So what did they do instead to explain how their pilots could see so well at night? They put out propaganda that British pilots eat carrots regularly, and carrots are filled with vitamin A, and vitamin A makes your night eyesight significantly better. That's actually just a lie. It's just not true. It's British propaganda that was used to explain why British pilots could see at night, and they weren't seeing, they were just using radar. So anyway, really neat historical anecdote. But if anybody tells you carrots make your eyesight better, they're lying to you. Not true. Vitamin A doesn't do that. Radar does. Anyway, that's just an aside. We're going to talk a lot more about light in the coming weeks, but we still have sound to talk about. So let's go back to sound. Change gears a little bit. We're going to talk about the interference effects that can be experienced with sound. And we'll continue with what we're talking about in the optional lecture on Monday. By the way, the material's not optional. Attending lecture will be. There will not be a quiz at the beginning of lecture next week on Monday because of the holiday. There will still be a lecture that I will hold. You can watch it at any time. You don't have to watch it during the lecture time, but there will be material. So we want to talk about interference effects, and like we talked about Wednesday, kind of one of the most useful and most interesting types of interference effects is the standing wave, right? So standing waves are super interesting because you can get like resonance effects, and we'll talk about that too. But you can get this strange phenomenon where the wave appears to not move, but it just oscillates up and down. And so the question is how do we apply our one-dimensional understanding of standing waves to three-dimensional sound, right? Sound propagates in a three-dimensional way, every which way. So we can't just talk about a cavity, right? Or actually we can. So the way that we talk about standing waves is just by using our one-dimensional understanding. And by the way, you can form three-dimensional standing waves. It's just a lot harder to understand, or a lot harder to derive mathematically. But you can still use the one-dimensional calculations that we use for standing waves, so long as you restrict your sound to only travel in one direction. And the way we do that is we only let the wave propagate in one direction. Only let the pressure wave expand in one direction. Now you might say, how do you do that? Pressure waves are going to do what pressure waves are going to do. Well, it's easy. You put stuff in the way. That is, you put sound in a hollow tube. So if the sound is in a hollow tube, the pressure wave can only go one direction. It can only expand and expand and contract in the direction of the tube. It can't expand the tube because the tube is made of metal or whatever it's made out of. So you can just do that, and then you can form standing waves in hollow tubes. And you can analyze them using the exact same calculations that we used for a standing wave on a string. The only thing that we need to be careful about is we need to make sure that we understand what is a free end and what is a fixed end for sound. So for a string, it was kind of obvious. Fixed end is when the string is fixed, so it doesn't move. A free end is when the string is free, so it does move. It turns out that we can actually come up with different answers depending on how we view the sound wave. So if we imagine that the sound wave is open to the air, I would love to share a GIF, but I still can't. Excellent. Okay. I'll have to figure out some way to fix this. I don't actually know what's wrong. It's just a matter, I think, my tablet being slow. If we imagine that the sound, that you have a tube with both ends being open to the atmosphere, well, what does the pressure do on the inside of our tube? So we have our tube open to the atmosphere on both sides. We have pressure waves moving through our tube. We have low pressure zones in the middle. But what about, so how would it make sense to say that this is a fixed or free end at all? Well, think about it this way. What's the pressure outside the tubes? Well, the pressure outside the tubes is whatever the pressure is. It's typically 1 atmosphere. If you're playing if you're putting air in your tube, you know, at sea level-ish. And so if the pressure outside of the tube is 1 atmosphere, and the pressure inside the tube is changing, well, once the air gets to the end of the tube, it can't just go straight from whatever it was to 1 atmosphere. It has to be continuous. Like the pressure is a continuous variable. Like the pressure shouldn't just jump places. It has to change smoothly. And so that means that the pressure at the end of the tube, at the interface between the end of the tube and the 1 atmospheric pressure air, it means that the pressure has to be at 1 atmosphere at the end. And so what this means is that, oh, let me write that down. Oh, okay. What this means is that the pressure at the ends and so, i.e., the pressure doesn't change at either end, which is to say that open to the atmosphere is equivalent to a fixed end for a pressure wave. Now, you might say, why would there be a reflection off of an open tube to begin with? Because remember, standing waves have to form as a result of reflections off of either end of the cavity. So how would there be reflection there at all? Wouldn't the sound just leave? Now, we mentioned that the sound waves, or that there is a reflection anytime the medium changes, right? When the medium changes, that's because the speed of sound changes, or the wave speed changes rather. And so we said, well, if the wave goes from fast to slow or slow to fast, then you'll get a reflection, and the reflection will either be inverted or not, depending on whether you went from slow to fast or fast to slow. But here, the sound wave speed isn't changing. It's still the speed of sound inside and outside. So why is there a reflection? Well, it turns out that our understanding of when reflections occur needed to be a little bit more nuanced. So really, the real answer is that a reflection occurs whenever the wave has to satisfy a different wave equation. So the easiest way for that to happen is when the wave satisfies the same type of wave equation, but just with a different speed, i.e. it's still a 1-dimensional wave equation, but the speed changed. In that case, the wave equation is different, so there would be a reflection. However, in this case, the wave speed is the same, but the wave goes from being a 1-dimensional wave to a 3-dimensional wave. And in that case, the wave equations are different. They like we just write out the wave equations in 1 and 3 dimensions. The wave equations are different. And so for that reason, we also get a reflection, because the wave, basically the wave can't just transfer all of its energy from in one wave equation form to another wave equation form without some of it being leaked back to the other side. And that's why we still get a reflection. Now, just as a reminder, the displacement wave, or rather the pressure wave, leads the displacement wave. And so what that means, and it's by pi over 2, it's by 1/4 of a period. So what that means is that open to the atmosphere is actually a free end if you consider the wave to be a displacement wave. And that should be kind of straightforward, right? The particles aren't being blocked when it's open to the atmosphere. So the particles can just oscillate back and forth in and out. That's no problem. And so in that case, you would have a free end because the particles are just free to move. Now, similarly, we can look at the case where it's closed to the atmosphere. Our pipe is closed. Well, when it's closed to the atmosphere, the pressure can be whatever it wants to be on the end. It's not restricted by the atmospheric pressure outside. So it'll just build, it'll get to the end, and then it won't have anywhere to go. So the trailing end will just build up the pressure, increasing the pressure, and then it'll bounce off because it'll expand back in the other direction. So this would be more akin to a fixed, sorry, a free end, and this is for pressure. And then we can do the same thing for the motion, and that one should also be intuitive. The particles, like if both ends are closed, the particles can't move outside. They just get stuck and then they bounce off. So this would be a fixed end for displacement. And this is just to say that free or fixed end doesn't actually mean anything physically, right? Because if it only just matters how you view the wave, then it doesn't matter. What does matter is whether you have two of the same type or two of the different types, right? We saw that if you have two free ends or two fixed ends for a standing wave, you get the same frequency inside the chamber, inside the cavity. The only time this happens is when you have the only time that you don't get the same frequencies is when you have a fixed end and a free end. And so it doesn't matter whether open to the atmosphere is free or fixed. It just matters that you use the same type of wave description, either displacement or pressure, for both ends. And you just have to be consistent. But going forward, we're just going to work with the pressure description of sound because it's kind of a little bit easier to visualize and easier to think about. Because really, when we're talking about particle displacement, we're talking about particles moving on average and they're moving away from an average position. It's just a little bit tricky. So I'm going to go over an anecdote. Not an anecdote, just some words. I'm not going to write this down, but it is written down in the lecture notes, just to briefly go over how instruments work. So an instrument, at least most instruments that function off of sound, or rather air oscillating in cavities, you think woodwinds, brass instruments, organs, those basically just produce their sound by some input of energy that excites sound waves in the instrument and then lets some of that energy out, either out of the top of a pipe organ or out of the end of a trombone or a flute or whatever. So let's just think about a trombone. So from the pressure perspective, one end is fixed, i.e. open to the atmosphere. This is the bell of the trombone, the part that flares out. And one end is free. This is the part that's close to the atmosphere. This would be the mouthpiece. This is the part that you put your mouth on, and the part that doesn't have access, like no air can go out of that from the cavity. It can only come in from the mouthpiece. So we can actually think about this, or think about and analyze the standing waves already in the trombone. Like once you put your mouth on the mouthpiece, you leave the other end open. It's one free end, one fixed end. And so we know what types of standing waves can exist in that trombone once we figure out how long the tubing is. The trouble is how do you actually get those standing waves going in the first place? I mean, we know what they'll do once they're inside. They're going to oscillate and they'll have some number of nodes, some number of antinodes, they'll have some frequency and so on. But to get them there is a little bit trickier to think of. By the way, I'll be done in a minute. So the trick is that by blowing into the mouthpiece, what we're doing is we're adding energy into the air. Now, you're not singing into the mouthpiece. You're not just letting sound waves of a certain frequency in. You're going like this, right? And so that's just that's sound waves of a whole bunch of different frequencies of all different types. It's probably relatively uniform even. And so what you're doing is you're introducing sound waves into the trombone of a whole bunch of frequencies. And then, well, some of those frequencies are going to bounce off the end of the fixed end, the bell, and then they'll reflect back and come back to your mouthpiece. And then they will constructively interfere because you're still buzzing on the mouthpiece. And so they will amplify as they bounce back because they have the right wavelength to constructively interfere. But most of the other waves that you're producing, they don't have the right wavelength. So they go to one end, they bounce off, and then they come back and they're at some other part in their wave. And so they don't constructively interfere. In fact, they will destructively interfere on average, especially because some of the energy leaves the trombone via the bell. They will destructively interfere. And so all you're left with is basically a filter or a resonating cavity where you input a whole bunch of different sound waves. And the only ones that survive in the trombone are the ones that can form standing waves. And then because the trombone's bell is indeed open to the atmosphere, some of those waves make it out, and then you hear that because it's only a partial reflection. And so what you're forming is a cavity or a resonance chamber where these sound waves are amplified, and so you just end up with basically the fundamental harmonics and then a few overtones. These are or the fundamental harmonic and then a few overtones. These are the higher harmonics. Now, the question then is how do trombones produce different sounds? And so there's a few ways that you could change the frequency that of a standing wave, but the easiest way is just changing the length. And that's exactly what trombones do. If you move the slide back and forth, the length of the standing wave cavity changes. And so the frequency that can be produced in that standing wave changes and you get a different tone. So that's how trombones work. And really that's how flutes and clarinets and all of those other woodwind and brass instruments work. They just work by changing the lengths. It's just for the woodwinds, usually you're pressing buttons that lets air out at different places rather than changing the length. Anyway, that takes us through to the end. I'm going to try to end the lecture here, if it'll let me. I'm just going to close it and then reopen it. So please stick around if it kicks me out.